the lectures related to the implantable kidney technologies and the perspectives of the future development of renal replacement therapy. And tonight, I would like to present a lecture for the possibilities of the future renal replacement therapy method development. And specifically, we will be talking about wearable and implantable artificial kidney technologies. Previously, we considered the conventional methods of renal replacement therapy. Specifically, we were talking about the hemodialysis briefly and about peritoneal dialysis without any deep diving into the topic. So we just discussed the main principles of the renal replacement therapies, how they are implemented in medical practice, and what physical principles lie behind the renal replacement therapy method. There are, of course, a variety of different modalities for hemodialysis and peritoneal dialysis, but unfortunately, it would be impossible to cover all modalities within one short course. And basically, what I wanted to explain tonight, yesterday we were talking about the main complication of the conventional renal replacement therapy methods. It's not just the safety measures, it's not just the effect on the physiology of the patient. It's basically the main issue with conventional methods of renal replacement therapy is the restriction of social mobility of the patient, and it's the lack of any continuous blood filtration, just like it happens in natural kidney. So basically, one of the main perspectives, one of the main future technologies that are supposed to solve this problem and provide the opportunity to actually maintain the continuous blood filtration is the development of the wearable and implantable apparatuses. So basically, this is a short evolution of renal replacement therapy methods. Here you can see the hemodialysis apparatus, the conventional method, and the next stage is development of the portable renal replacement therapy devices. There are actually two generations of those devices. The first generation is the portable hemodialysis apparatuses that weigh about 10 to 15 kilograms. They can position within the apartment of the patient, and basically a patient has an opportunity to perform this procedure at home. The second generation of portable kidneys are actually even lighter in comparison with the first generation. It's about 1.5 kilograms, 2 kilograms. And basically they have the same purpose as the previous portable kidneys, is just the miniaturization of these systems. And the next stages basically is the development of wearable artificial kidney and implantable artificial kidneys. And the main purpose for developing these types of devices to improve the social mobility of the patient. So basically, it's an attempt to make a continuous renal replacement therapy, whether by means of dialysis regeneration or by means of imitating the native nephron of the human organism. So basically, if we try to find the main difference between those two approaches, so how do we make a wearable artificial kidney, for instance, is basically a continuation of the conventional dialysis methods, with the only difference that we have to decrease the amount of dialysis that we use per procedure. So it basically requires a specific dialysis regeneration unit that will provide the continuous regeneration of that solution that will be able to be used in the second cycle and in next cycles of renal replacement therapy. The implantable artificial kidney is basically the technology that is supposed to imitate the way how the native nephron functions. So in the first lecture, we had a brief description of what nephron is as the structural unit of kidney. And basically, we simplified the blood filtration as the three-stage process, even four-stage process. It's an initial blood filtration when we in Bowman space, there is a primal urine that's generated due to transmembrane pressure. Then there is a reabsorption and water reabsorption and nutrient reabsorption in proximal convoluted tubule, specifically in Henle loop. Then it's secretion in the collecting duct. And finally, it's a secretion, the final product, the final urine exits from patient due to natural process. And basically the main idea behind the implantable kidney is to recreate and imitate the way how this apparatus, how the native nephron is actually functioning. So we basically have to imitate the Bowman space, the glomerular and the proximal convoluted tubule in case of the filtration and the further reabsorption. In case of variable artificial kidney, it's basically the same approach as hemodialysis or peritoneal dialysis. So if we can decompose the main idea behind the variable artificial kidney, and this lecture will be more focused on dialysis regeneration method to amplify the difference between implantable kidney and variable kidney during the next lecture that will be dedicated specifically to implantable kidney technology. So basically, we try to improve the conventional method by introducing the dialysis regeneration unit that provides a continuous regeneration of dialysis fluid. That means that we will not require to use a very big amount of dialysis fluid, such as in hemodialysis, when we have to waste about to spend about 120, 150 liters per patient. Here, we assume that we can create a small dialysis unit that will regenerate a very restricted amount of dialysis, about 1 liter, that will be continuously circulate through the mass exchange unit. And by means of dialysis regeneration, we will remain the filtration rate and ultrafiltration rate by means of removing uric toxins and excessive fluid. The same idea goes for peritoneal dialysis. So in peritoneal dialysis, we have to constantly change the solution for peritoneal dialysis to make sure that we will maintain ultrafiltration and detoxification of the human body. Because in case of peritoneal dialysis, we use a very restricted amount of peritoneal solution per procedure, about 2.5 liters. And that means that we have to constantly exchange this solution about 4 to 6 hours, every 4 or 6 hours. That depends on the membrane properties of the patient. And the idea of dialysis regeneration is basically the same. We are trying to extend the procedure by means of constant dialysis regeneration. So we develop a specific dialysis regeneration unit with the purpose to remove all toxins from that solution by reintroduce the osmotic pressure. So we will continue the ultrafiltration process, because the main physical principle, so to speak, behind the ultrafiltration is actually we create the gradient of osmotic pressure by introducing the osmotic agents such as glucose. And if we deplete the glucose, if the concentration of glucose in the peritoneal solution and the patient's blood becomes even, that means there will be no ultrafiltration, and due to lymphatic flow, this solution will start to go back into patient, which is basically a very critical condition that we cannot allow to happen. And here you can see some examples of how variable artificial kidney looks in forms of prototype. Here you can see the VAX system that has been developed in the Californian University. Here you can see the dialysate regeneration unit, the mass exchange unit, the different sensors and equipment that provides the adequate functioning of this apparatus. Specifically in this lecture, we will emphasize our attention on this particular dialysate regeneration unit, because we have to develop some physical and chemical principles behind the dialysate regeneration that will provide the constant removal of uremic toxins, and that will provide the ultrafiltration flow. And basically, it's one of the most critical parts of variable artificial kidney. On the left side, on the picture B, you can see the prototype of automated variable artificial kidney developed in Singapore. It's basically one of the apparatuses that is close to its final stage. So there are already prototypes that were tested. In both cases, they were tested in patients at some point. And the most essential parts of both apparatuses, despite the fact that they are developed for different dialysis methods. So this apparatus is developed for hemodialysis. You can even say it by looking at this mass exchange unit. And this specific apparatus was developed for peritoneal dialysis. So no matter what way we choose, we have to consider that in that case, we need to constantly regenerate dialysis one way or another. So let's stop on the dialysate regeneration method. If we want to develop a dialysate regeneration unit that provides a continuous procedure of renal replacement therapy, we have to consider methods that will help us to remove the toxins that we receive from the patient. And speaking of different methods, to emphasize why exactly we have such strange methods like electrochemical oxidation method or enzymatic method or even thermal method. So the first question we have, why we cannot just use a number of different sorbent systems, ion exchange resins, etc., to provide an adequate regeneration of dialysis. The problem is that we have a lot of small solute toxins, and to be more specific, we can look at the nitrogen-bound metabolite called urea, which is basically a small-sized molecule. It's about the molar mass of urea will be about 60 grams per mole. With the generation rate for different patients, this number can vary, of course, but I will just use some mean numbers, about 20 to 40 grams per 24 hours. So this metabolite is been generated quite fast in the human organism, and the concentration of this metabolite can increase quite rapidly. And due to the fact that it's a very small-sized molecule, if we use the conventional types of activated carbon, usually we have to consider a very huge sorbent column to deal with such generation rate to effectively remove this kind of toxin. We need to build very sizable sorbent columns. That's why we need to develop specific strategies to deal exactly with this metabolite. So we need to develop urea removal strategies that will not require a huge size sorbent columns, because otherwise we will not be able to create a variable artificial kidney. The main idea behind variable artificial kidney is its size and its weight. If we have a lot of sorbent, that means that we have a very massive dialysate regeneration unit. That means that this apparatus will not be variable for a patient anymore. So for these strategies, different approaches were used. The most prominent approach is enzymatic method. Basically, we use urease as the enzyme that catalyzes the urea hydrolysis. And this method basically is being used in both variations of this apparatus. And the main idea that we introduce in the system enzyme, by one mean or another, it speeds up the hydrolysis of urea. We then use the sorbent method to remove the byproducts of the urea hydrolysis, and then we return the regenerated solution back to the system. Electrochemical method is another approach to eliminate the urea by means of direct anode oxidation of this particular metabolite. It's not selective in comparison with the enzymatic method because the introduction of different substrates in the solution can lead to the anode oxidation of basically those dialysate components as well. For instance, if we have the chlorine ion, it will be oxidized to the chlorine gas. And if we have the glucose, it will be oxidized or decomposed to methyl glyoxal and different components that can be the byproducts of glucose electrochemical oxidation. And last but not least is the thermal method. Is basically the idea that we can heat up the dialysate solution, and in the condition when we have the temperature of the dialysate in a specific container about 150 Celsius degrees, we can promote the thermolysis of this metabolite. That's, well, quite obvious. If we use the thermal method, we consider that we need a heat up unit, we need a cooling system. That means that this method is not applicable in case of development of variable artificial kidney, because this system that's supposed to be maintain the thermolysis of urea will be very massive in comparison with enzymatic method, which can be implemented by introducing a very small column with immobilized enzyme, and electrochemical oxidation method where the size of the electrochemical cell can be relatively small as well. So there are requirements that should be taken into consideration for variable artificial kidney. Just like for any type of medical apparatus, we have to consider the safety issues, and depending on what particular method we use as the basis of that method, whether it's a hemodialysis or peritoneal dialysis, we have to update the list of requirements that should be met for this apparatus. Well, the common demands are usually is that apparatus has to be ergonomic. That means it has to be very light. It should be even less than 5 kilograms, something about 1 or 2 kilograms. Considering that we will introduce the dialysate solution, this system will become heavier. So we cannot accept the idea that this apparatus can be 5 kilograms or even more. So it would be more preferable if it was lighter, much lighter than 5 kilograms, about 1 or 2. The dialysate volume has to be minimal as well, because if we introduce a decent amount of dialysate solution, like 2 liters or more, it will affect the ergonomics of the system as well, and it will be very hard for a patient to operate this system. Other common demands is this apparatus basically has to work longer than conventional hemodialysis or peritoneal dialysis method. So it's expected that with dialysate regeneration unit, we can make a step further to continuous blood regeneration in a form that we can perform the dialysate, the renal replacement therapy for at least 12 hours or even more without recharging the system. Other common sense demands is, of course, that this variable artificial kidney shall not affect the blood composition, pH, and other blood parameters in the slightest. Because in case of when we introduce the dialysate regeneration method, and when we start using and utilizing different physical and chemical approaches to cope with the uremic toxins, that means that we can create some unwanted byproducts that can contaminate human blood. For instance, in case of enzymatic method, we will deal with the ammonia ion, which basically should be removed from the system before it goes to the human blood. In case of the electrochemical method, we will generate a lot of gases like nitrogen, hydrogen, oxygen, carbon monoxide, dioxide, etc., and so on. So in that case, we have to consider the debubbling system that will remove these gases, and we need to consider a degassing unit that will remove these gases that were that are presented in the solution in soluble form. In case of uremic toxins, we have to consider that we have to remove all the markers like urea, creatinine, uric acid, bilirubin. We need to deal with nitrates and phosphates. Different aromatic and protein-bound substrates should be removed one way or another, including picrazole and phenol. We have to deal with excessive ions such as potassium. In some cases, we have to remove the extra sodium if it's required. And it should be emphasized that considering that we develop the variable artificial kidneys for different modalities of dialysis, we have to add additional requirements. For instance, if we take into consideration peritoneal dialysis, and in peritoneal dialysis, we perform ultrafiltration by introducing the glucose, the osmotic agent. That means if our dialysate regeneration unit severely affects the concentration of this particular osmotic agent, we have to reintroduce this osmotic agent one way or another to increase the concentration of this glucose to maintain the ultrafiltration flow. Otherwise, if we deplete the concentration of glucose, we will deal with situation when lymphatic system will just return the solution back to the patient. So in that case, we have to consider that glucose by natural means, it diffuses in the human blood within the peritoneal cavity. And we also introduce the dialysate regeneration unit that can affect the glucose concentration by means of, for instance, adsorption of this osmotic agent on activated carbon, or there could be some method that can affect the glucose concentration by means, for instance, electrochemical decomposition. So this particular demand has to be taken into consideration because ultrafiltration is a critical issue of peritoneal dialysis and basically any other type of dialysis. And the depletion of this particular osmotic agent can be critical for the functioning of the apparatus and for the health state of the patient. So we shall not harm the patient by just removing all glucose and providing the opportunity for lymphatic system to hydrate body again by returning all liquid back to the human body. Here you can see the decomposition of these particular methods. So when we talk about enzymatic method, that's basically the ready regenerative dialysis system that was introduced into hemodialysis about 40 years ago in the United States of America. And basically the main idea is that we have the first layer of ureas that is immobilized on some substrate. The spent dialysate goes from the patient to this ready system. Ureas provokes the catalysis of urea hydrolysis. Then we have different ion exchange layers that provide us to remove the ammonia ion that is basically the main byproduct of urea hydrolysis. And we have activated carbon to basically remove other substrates like creatinine, uric acid, and other uremic toxins that can be presented within the spent dialysate solution. Electrolysis or electrochemical method. The main part of this particular unit is electrolyzer. So there should be an electrolyzer cell that helps us to deal with the high concentration of urea when it goes from dialyzer or patient. We have basically two sorbent units. So there is a pre-sorbent unit that helps us to deal with multiple toxins like creatinine and uric acid. The electrolyzer is specialized in electrochemical urea oxidation. Unfortunately, unlike enzymatic method, it's not selective. That means that if there are some other components of the dialyzer that go to electrolyzer, they will be anodically oxidized, or there will be a reduction reaction on cathode surface. So we have to deal with byproducts of the electrolysis. That means that we need to introduce the second sorbent unit or some mass exchange unit, ion exchange unit that will help us to deal with the byproducts of the electrolysis. And of course, because we generate a lot of gases by introducing into the system nitrogen, hydrogen, carbon dioxide, chlorine gas, etc., we need a degassing unit and debubbling unit to remove all gases from the system. Otherwise, these bubbles will go back to the patient, and that's a very dangerous situation. And last but not least, it's a thermic method. We have a heater. We have different heat exchangers that help us to basically provoke the thermolysis of urea. This method can be applied to stationary hemodialysis systems, but because it's a very because of power consumption and overall size of this method, in case of wearable artificial kidney, there is no way we can apply it to wearable devices because we are very restricted in terms of ergonomics. This apparatus shall not be heavy. This is the main idea behind the sorbent method. You can see the Langmuir theory here. So we actually rely on the adsorption of the substrate on the active center of the activated carbon. And by using this method, we can actually make a prognosis or a mathematical model that helps us to predict how this concentration or how the absorption speed will change in time. There is a small comparison of different modification of carbon activated carbons. So when we talk about the creatinine elimination and uric acid elimination, they are basically, no matter what activated carbon we choose, usually we can use the coconut activated carbon of different modifications. They basically provide a more or less effective decrease of these metabolites. But in terms of urea, they have very small absorption, specific absorption. So we can basically absorb only 6 milligrams of urea per 1 gram of the sorbent. And if we calculate the cumulative amount of sorbent or mass of sorbent that we have to use to implement this specific method, it will be a few kilograms of the sorbent at very least. That means that unit, the dialysis regeneration unit itself will exceed the mass parameter that we shall not violate during the development of wearable artificial kidney. That's the principle of the enzymatic method. So it's just the small decomposition of what we just said, with the only exception that there is activated carbon that goes before the immobilized ureas. And here you can see the main reaction that goes in a slightly acidified medium. So we generate the ammonia ion and the bicarbonate ion. And this type of byproduct that we have to deal with somehow, because we have to remove this ion before it goes back to the patient. We have the ion exchangers that help us to deal with the byproducts of the enzymatic method, activated carbon again, and we have to reintroduce the calcium, magnesium, and potassium, because if we have the ion exchanger, there is a big chance that we will significantly decrease or affect the concentration of very critical ions that will be very harmful for a patient if we just remove these ions constantly by means of dialysis regeneration. The big advantage of that method is that it's selective. The ureas will perform the catalysis of urea only. That means that we shall not be worried about other substrates that can be affected by the urea's presence. And that's why it's so preferable in case of the dialysate variable artificial kidney systems that implement that method. The selectivity is this method is the biggest advantage of that method. This is the main principle of electrochemical oxidation method. We basically rely on direct urea oxidation. And as you can see, if we talk about acidified method, we, in case of urea anode oxidation, acquire a huge amount of different gases, such as hydrogen, nitrogen gas, the carbon dioxide, oxygen, chlorine gas, and there are some possibilities that urea hydrolysis will take in place in the acidified medium with the formation of the same ammonia ion. There is a hypothesis that we can actually affect urea by cathode reduction in the presence of the atom hydrogen. There is the reaction with hypochlorous acid that again generates the nitrogen and dioxide gas. So basically it's a method that is not very selective, so it will react with other components of the spent dialysis solution. I think it's not presented on those slides, but basically if we talk about, for instance, the chlorine ion, one of the key ions that are presented in the dialysis solution, by means of direct anode oxidation of this ion, we will generate the chlorine gas. So basically, with the high concentration of this gas, of this ion, we will affect the concentration of this ion, and we will generate the additional gas that we have to deal with somehow. Yeah. Speaking of the efficiency of this method, it mostly depends on the type of material and the properties of electrochemical cell and the current density that we apply for this method. It depends on the composition of the dialysis solution. It's very sensitive to the change of the pH of the solution. For instance, if we talk about graphite and we have the bicarbonate solution that is alkaline solution in comparison with standard glucose solution, the efficiency of this method will be lower in comparison if we work with graphite in the acidified solution with glucose. But we will talk about the introduction of different materials. And if we talk about, for instance, graphite and platinum electrodes and different modifications of silicium and carbon foam, that you can see that if we make some specific urea elimination rate that helps us to evaluate the efficiency of this method, then we should consider that the material will affect this problem very significantly. And there is also a chance that if we introduce a different type of material, so for instance, the platinum type electrodes, in case of platinum, it will catalyze the oxidation of chlorine ion, and basically it will generate more hypochlorine ion and chlorine gas in comparison with graphite, which does not affect the concentration of this particular substrates well in such rate as the platinum electrodes will do. This is the decomposition specifically of anode urea oxidation. So if we look at different types of medium, like acidic medium, the neutral medium, the alkaline medium, the byproducts will be different. So we have to take into consideration that if we work with different types of media, which is basically the case in terms of peritoneal dialysis or hemodialysis, for instance, acidified medium will be used for glucose solutions because glucose is more stable in a slightly acidified medium. The neutral medium is basically a typical solution for hemodialysis, and the alkaline medium can be also presented if we deal with the solution that goes back from patient from peritoneal cavity. In all cases, we will have different byproducts, and different types of reactions with some alterations, and that's the problem that we have to take into consideration. A very huge issue that I just marked out for electrochemical method is the lack of any selectivity of that method, especially if we use a very high current density approach. So there was a hypothesis that we can basically find the potential of the working electrode that will help us to avoid the oxidation of chlorine ion and the formation of hypochlorite ion. And basically, the main idea behind that was to find the potential before 1 volt, because after we exceed the potential of 1 volt, we will deal with other side reactions that will take place in the solution, including the generation of hypochlorine and chlorine gas. This theory, this hypothesis was not be proved by experimental methods. So here we tried to implement the 3-electrode approach for cyclic voltammetry. And for different types of electrodes, we were trying to find the specific potential that would help us to eliminate this urea without introducing other types of reaction. Unfortunately, it was not the case. There were no any signs of the urea reaction. Urea slightly affected the form of the cyclic voltammetries, but that was pretty much it. So the only solution was to use a very high current density that increased the potential of the working electrodes above 1 volt. It was about 3 to 4 volts. And here you can see just a graphical illustration of how different materials can affect the concentration of urea. So the critical issue here is to choose a specific electrode material type that will help us to cope with high urea concentration. So there are multiple disadvantages of this method, which make it much weaker in comparison with enzymatic method. The biggest issue that we have here is that this method is non-selective, unlike the enzymatic method that will help the system remove urea without provoking any side reactions. So one of the most critical reactions that we have to deal with, and I will reference Van Gelder, who actually made a great research on that topic of how electrochemical method affects the concentration of glucose and how the electrochemical generates additional byproducts of urea electrochemical decomposition. So we have to deal with glyoxide and methyl glyoxide. And if we talk about the concentration of these byproducts in peritoneal solution, for instance, is drastically increases when we introduce the glucose into the system. And of course, because we have the peritoneal cavity and all these substrates will go back to the patient, those basically are small-sized molecules. We will experience the increase of those particular substrates in plasma. And what's worse, those are small-sized molecules that we cannot deal with by means of sorbent method, because the generation rate is so high for this particular reaction that we have to develop very decent, very sizable sorbent unit again to deal with the byproducts of electrochemical oxidation of the glucose, which basically sends us back to the blueprint idea of how to regenerate dialysis. So basically, if we talk about the most prospective methods of variable artificial kidney and dialysis regeneration, enzymatic method is probably the most prominent method right now. That's another disadvantage for electrochemical method. If we deal with the peritoneal dialysis, and if we remember the 3-pore module for the transport of solutes in the peritoneal cavity, in case of peritoneal dialysis, we have a huge size pores that allow big sized molecules by means of conventional transport go to peritoneal solution, such as albumin. And albumin is basically a type of protein that that when we introduce this albumin into the peritoneal solution and we send this peritoneal solution to electrochemical cell, we basically experience a very sizable foam formation. So we generate such amount of different gases and foam that we cannot actually use debubbler effectively. That means that in order to implement the electrochemical method here, we have to use a additional mass exchange unit that prevents the appearance of the albumin at the dilysate regeneration unit, which makes the dilysate regeneration unit even bigger in comparison with enzymatic approach. That's basically the description of how we can present the biotechnical system of wearable artificial kidney. And biotechnical means that we have the two systems to deal with. It's a biological system that we have to treat from chronic kidney disease by means of renal replacement therapy. And it's a technological system that basically performs the renal replacement therapy, and it includes the dilysate regeneration unit. In case of this particular presentation, I provide the results of the experiment with electrochemical approach. That was the result of our long-term research of that method. And basically, what we have to take into consideration that we have to remotely control this system, because there are many issues that have to be taken into consideration, and we have to disable this apparatus if some malfunction happens. So here you can see the dialyzer, this mass exchange unit we need specifically to prevent the generation of the foam, because when we deal with peritoneal dialysis, we will acquire a lot of albumin and proteins that will go to the dilysate regeneration unit. And if there is a direct connection here, we will deal with the foaming. So we introduce this mass exchange unit that does not allow these proteins go further into dilysate regeneration unit, and we deal with other types of the toxins that we have to remove from the system. Yeah, those are results that were obtained for a big animal module. We were testing those particular apparatuses on pigs, and pigs are actually preferable for this particular method because the peritoneal cavity is very close in an anatomical sense to a human peritoneal cavity. And here we implemented different types of experiment, including the control experiment of what happens if we just remove kidneys and we do not affect the animal model in any way or another. So in case of the removed kidneys, we have a very sharp decrease of creatinine, we have very sharp increase of urea, decrease of proteins, and it also affected different parameters like alpha microglobulin and beta microglobulin. And we performed two types of experiments, like we imitated the acute kidney failure by introducing a specific drug that actually shut down kidneys for a very short time. And we imitated the terminal kidney disease by removing kidneys from the animal. And basically what we observed here is that in terms of acute kidney disease, we could deal with the high concentration of creatinine. There was a small increase of urea, basically affected by the fact that if we have very small concentration of urea, there will be basically redistribution of charges during the electrochemical method. That means that other reaction will be dominant in comparison with urea oxidation. We also did not affect the total protein and albumin in a very critical manner. In terms of the chronic kidney disease, we basically could remove a small amount of urea by introducing an electrochemical method, because after we remove kidney, we start to experience the urea concentration, and we could cope with creatinine at some point. Like one of the biggest problems with wearable artificial kidneys right now is the creatinine clearance. It's the problem that should be solved during the further development of these apparatuses. Yeah, that's just the parameters of our apparatus. Like it was about 2.5 kilograms without any additional equipment, and 5 kilograms when it was fully assembled. the estimate annual cost, like the main advantage of wearable artificial kidney, it should be relatively cheaper in comparison with conventional methods where we have to consider the constant dialysis production and constant water purification in case of hemodialysis. These are comparison of different wearable artificial kidney apparatuses. As you can see, the vast majority of them uses the combination of sorption method and enzymatic method. And there are some apparatuses that implement the sorption method. And the preclinical trials were, this is a little bit outdated table. They already finished the preclinical trials, so they actually approved this apparatus. So they already tested this apparatus on animals and some patients, and basically this apparatus was certified. Basically, they are very close to introduce this apparatus to the market. Yeah, to summarize the main points of this presentation, excuse me. The core difference between wearable artificial kidney and implantable artificial kidney is basically in terms of implantable artificial kidney, the main idea is imitating of the nephron as the structural unit, while wearable artificial kidney is more a continuation of the conventional methods that introduces the dialysis regeneration method as the essential part of the kidney miniaturization, while implantable artificial kidney has to provide a continuous blood filtration, basically the thing that cannot be affordable even in case of wearable artificial kidney, because you still have to exchange the dialysis solution. You cannot permanently use the same solution during the dialysis procedure. In case of implantable artificial kidney, there is a need to develop a system that will fully imitate nephron, both in blood filtration and reabsorption process. That's basically my whole presentation. If you have any questions, I will be glad to answer them. Thank you. Yeah. Yeah. We go to the next lecture. No questions?
Question from for this session. If you have any questions, you can ask them. Yes. There's a question.
Yeah.
So using the electrolysis method, does it require bigger? Okay. So does using the electrolysis method, does it require a bigger energy source, like in terms of, let's say, bigger battery or something similar?
Yes, it will require additional power supply, which makes it less preferable in comparison with enzymatic method. Because in terms of enzymatic method, we just have a modified sorbent column that has the enzyme in it, and all we have to do is to power pumps that actually recirculate the spent dialysis through this column. In terms of electrolysis, we have to supply electrochemical cell so we can perform the electrochemical decomposition of the different toxins within this system. So basically, yes, we require additional power supply, and usually the power consumption does not allow us to exceed the exploitation of this particular method more than 8 hours, which is another basically disadvantage. Yeah, that's actually a good point that you made, that we need additional power supply to actually implement this method. It's not as catastrophical as in comparison with thermal method, where we have to heat up the solution and cool it down, but still the power supply is essential problem here that has to be addressed.
So how about the combination of electrolysis and sorption methods?
Well, basically, that's the only way how we can implement this method, because when we deal with the electrochemical method, we cannot use it all alone, because we will generate the hypochlorine ion, we will generate different gases, we will generate some byproducts that have to be dealt with. And usually, the standard implementation of this method includes the sorption method that helps us to cope with byproducts of electrochemical decomposition of different parts of the dialysis solution. So basically, the only way we can implement this method is the combination of sorption method and electrolysis. At least we implemented it when we were working with a prototype for wearable artificial kidney within our project in our university.
So, just one final question.
Mhm.
So as I understand, the electrolysis method produces a lot of different byproducts, which changes the pH of the
Yeah.
dialysate, if I remember. I also remember there was a slide that showed the the chemical reactions in 3 different mediums are different.
This one.
Yes, yes. Thank you. So is it possible that, with, let's say, with longer operation of this, that the actual electrochemical reaction essentially changes because the pH of the medium keeps changing?
Yeah, that's a possible outcome because, for instance, if we choose the platinum electrodes, they will acidified solution, and if we do not have any additional sorbent or resin, some ion exchange resin that will fix the pH of the solution, that means that we will further acidify the solution, thus changing the reactions that might take place during the electrolysis method. It does not just concern the urea oxidation. It concerns other reactions that can be amplified by the changing of the pH of the solution.
Thank you.
Yeah, thank you.
I think then we can give some hybrid splits. There's a tea outside, we can for all the participants. Then after 5 minutes,